Hi everyone, welcome to today's session on VLSI Design Flow by VLSI Deep Dive. In today's session, I'll be talking about VLSI Design Flow, also what are the career opportunities in VLSI and semiconductor. If you have any questions, please feel free to type in the chat window, and I'll answer those questions as soon as I can. So, what comes to your mind when you think about electronics product, right? Think about what would you want in a mobile phone, right? As in, you want your mobile phone to be fast, that corresponds to a good processor, lots of RAM, that corresponds to memory. You want to play games, you want to store a lot of photos, so that corresponds to the disk size. You want to take a good photos, that corresponds to camera. You want to play games, watch movies, Netflix at the fastest speed, that corresponds to what is modem. You want to use maps to go from one place to another, that corresponds to GPS in a mobile phone. And you want to probably charge it once a day or once every 2 days, that corresponds to long lasting battery in a phone, right? All these are semiconductor components. All these are semiconductor chips. A mobile phone is primarily made of semiconductor chips. These chips are connected together. Some of these are, as in a lot of these components are within one chip, and a lot of time these multiple chips are connected together. So all these electronics product is primarily made of semiconductor chips. Okay, think about RAMs, modems, your battery controller, your image sensors, storage, all these are semiconductor chips. So building a phone like these days is like assembling semiconductor Lego blocks, or what is also known as chips. Types of semiconductor chips, right? As in, there are logic chips. Logic chips means if there's some logic function like processing. Some of the companies which do make processing or processors are Intel, AMD, Nvidia also makes computing elements, Apple, and then modem. Qualcomm makes it modem, which allows you to get 5G data, 4G data, and Samsung. Then other kind of chips which are there are memory chips. Memory chips are like your uh, your disk space, your RAM, which allows you to run faster, or your storage where you're storing your photos. So memory chips companies are like Samsung, Hynix, Micron, SanDisk, or what is also now known as Western Digital, Toshiba, again Samsung, and memory. So there are multiple kind of memory chips also in your cell phone. All these are semiconductor components. Then you have analog or RF chips. What are analog or RF chips? Where you deal with the physical world, physical analog world, like wireless signals, power management, those kind of chips. Or you want to be, for example, your access card in your office, they use NFC, or your chips or credit card these days has NFC. So all these are, there are multiple companies working in this, analog devices, Maxim, ST Microelectronics, Texas Instruments, NXP, Broadcom, Qualcomm, On Micro, analog devices. So multiple chip companies also working in this area. Then there are sensor chips. You have sensors in your watch, you have sensors in your camera. What are the companies which are working on this? Samsung, Nikon, Sony, Infineon, Synaptics, Goodix. So a lot of companies also work in India. The good part is most of these companies also have design houses in India itself. So this is what a phone looks like. In a phone, you have multiple semiconductor chips. They're combined together to make a phone or a device. And some of these chips actually are SoC, which are system within a chip itself. So let's understand using a flow what happens within these chips. So let's take an example of iPhone 14 Pro. As in, there is a RF front-end chip from Broadcom or Avago. There is a chip from Skywork. There is a chip from Qualcomm. There is a microcontroller from ST. There is PMIC chip from Qualcomm. There is, so you can see multiple companies come together to create these massive phones or devices. And semiconductor chip designing is the flow is understanding how these chips are made. Each of these chips design is done in India nowadays. So let's so inside a chip, what happens, right? As in, what is the technology which is used? Silicon is converted into these chips. Silicon is converted into these things. Then wafers are created. Those wafers are fabricated, tested, and this is how these chips are created. So technology, right? What you must have heard about that, no, something called technology. There are multiple technology nodes. So this is basically what is the gate level, gate pitch. Different some of the companies use different terminology, but this is what a technology node means. Right now we are close to these technology nodes have been shrinking over years. We're now close to 2 or 3 nanometer technology nodes now. Now let's understand the VLSI design flow. But before we get into that, is understand what are the key elements of a chip. So we talked about cell phone, right? You have seen cell phone has multiple kind of elements. Let's understand key elements of a chip. One key element is logic gates, which are your AND or gates, which you would have studied in your college. Then there are macros like CPU, IP, FIS5, 5G modems. There are memories. These also take a lot of space. And then other common component is IOs, which allows you to communicate with the outside world. Now, what happens when you would have seen, right, people creating, showing images of a chip which where different logic elements are placed. So you basically place these logic elements, as in you, for standardization, you will put them in a row. Once you place this, the chips, and then connect the power, the chip starts to look something like this. And this is the kind of images you would have seen when people are sharing it. This is nothing but these logic elements put in these chips, and then all the hard components, input output connected, then red and gray stands for power connectivity. And that's where how a physical layout or physical design of a chip looks like, and this is what goes into fabrication. So you would have seen these kind of pictures of chips. It's hard to imagine from here what is that chip looks like, but this is what is going on under the hood. You're placing logic elements, you're placing common components, RAM, CPUs, connecting them with power. And this is how it's very dense, because there are a lot of millions of transistors, billions of transistors in a chip these days, and this is how it looks like. If you have any question, just type it in the chat window and I'll answer those questions. Okay, so how chips are made, right? As in, so basically you start with system specification, you design your architecture, you design, write your RTL. So this is known as the front end part of the design. This is like, it's not like you are connecting wires. This is like something similar to, very similar to software coding. You're writing a code, you're using EDA software to compile that code and implement that code. So these steps, first few steps till physical design, is typically what is known as front end part of the chip. And then after physical design, it's known as back end part of the chip design. The front end part of the design, the front end part of the design, are you able to see that slides are being updated? Just type it in the chat window. As in, I'm moving the slide. You're still seeing the first slide? Okay. Okay, so maybe who was it? Rajini, I think it's your end. Other people are able to see the slides being updated. Okay, so then the physical design part of the chip is the back end part after physical design. So what is the difference between front end and back end? Mostly front end part is independent of the technology. For example, if you write a Verilog code, it's not the same Verilog code can be for 2 nanometer or 10 nanometer or 90 nanometer technology. What was once you go into physical part of the design, it is starts to get linked to a particular technology node, whether it's 9 nanometer and 2 nanometer, 90 nanometer, so 45 nanometer. So physical backend part of the chip design flow is linked to a particular technology node, linked to a particular fabrication, linked to a particular foundry, where front end is typically independent of the foundry. So EDA software is like compiler for the software code. But so you, if you have written like a code, C code, right? Typically, you will have a compiler, and this job is done by EDA companies like Synopsys is there, Menta Graphics is there, Real Intent is there, the multiple EDA companies. They take your software code or RTL code and convert that into these chips which we have been talking about. So it's not very different from software programming. So your software takes compiler and creates an executable which you run on your PC or cloud. Similarly, EDA software converts the design which you have written into physical design, which then goes into Foundry. So EDA software is like compiler for the software code. So chip design flow, let's talk about. You start with specification, then you architecture, then you integrate the SoC, you do verification of that, you do synthesis. We'll go into each of these steps also a little bit more detail. Then you do timing analysis. Now, after verification, logic synthesis, this is where your backend starts. Go into place and route, go into static timing analysis, sign off, gate level verification, and then you tape out the chip and give it to the foundry for fabrication. After that, testing and packaging is done. So what is specification, right? Specification represents customer requirement, as what are the functions or features I want in a product. Or if from a chip point of view, it will be what, how many input or output pins will be there in the chip, what technology node I'll be working on, what will be the functionality on a chip. That is what is known as specification. Based upon that specification, you figure out, okay, what are the various components I will need. For example, if you're designing a counter, maybe you need a timer in your chip, or you need a clock in your chip. After that, let's say you want to design, okay, I have a screen on my phone and this screen turns off after a certain time. So how, for that you need to design a counter. So let's say your clock is running at a particular frequency, but you need to then design a counter to count for a particular time. And after that time, you turn off the screen. So this is what is known as architecture. You have a functionality that I want to implement a screen turn off, but for that you get into what are the components you will need, and that is known as architecture. So you'll need a counter, what are other components you'll need, how these will be connected together. Once architecture is done, then you start doing RTL coding. This is something which you have learned in your college, or you would be learning in your college. Writing a Verilog, VHDL, Verilog is used most commonly these days. This is not different from writing software code. This is what a lot of chip designers do. Anyone can do, as in, if you have an inclination towards hardware design, you can very easily write Verilog code. And once you start learning, you can write complex Verilog codes as well. But a lot of chip designers do, where you start basically writing Verilog code, and this is not different from not very different from writing a software code. And once RTL coding is done, you basically, when whatever code you have written, you have to verify, right? As in, you have to make sure it is working. And this is one of the hottest job in chip design: verification, verifying the RTL code which is written, verifying the functionality which has been written. And it's not very different from verifying a software code, just that terminologies used are different, the languages you may be used which are different, but it's not very different from doing a verification of a software code. It's actually much more rewarding, both financially and as in, if you like, debugging. So this is what a lot of engineers sitting in India and worldwide do. Verification, typically it's 50% of the workforce is verification engineers. Then once verification is done, what do? You basically convert that into gates. So long before 30 years ago, you used to basically create gates yourself from a Verilog code or from the functionality. Nowadays, you write at a more abstraction level, which is saying is RTL coding. And then after RTL coding, then a software tool will convert that your code into a gates, and or gates, flip flop, primary functional element. And it's yeah, like your compiler, right? Its compiler is converting your Python or whatever code it is to object file. Similarly, it's converting RTL to synthesis. So there is a question why number of RTL engineers are lesser. This is because For example, let's say you have this is because a lot of the chips these days, you use existing IPs. Okay, for example, what I mean by existing IPs is, for example, processor, right? Same processor may be used in multiple chips. Okay, so you need to design processor only once, or maybe modify a little bit, but each of the chip needs to be separately verified. So you can imagine, right, as an CPU design, maybe let's say 10 people do, or maybe 50 people do, but this goes into, let's say, 500 chips. Then each of those 500 chips are verified separately, have to be verified separately. So that's why verification engineers typically are more than RTL engineers. But a lot of time, RTL engineers also do verification. So verification is one of the important part of the chip design, and there are more. Now, after that, when you want to test a chip, okay, basically, let's say chip is created and you want to test it, you will probably probe some signals and figure out, okay, whether, if it's not working, you will reject it. If it's working, you will pass it and ship it to the customer. But this chip design, right, is happens to do chip design or testing. We have to tap these wires like you would have done in a board design, and make sure every signal which is supposed to get, every place which is supposed to get zero, supposed to get one, you're getting those zeros and ones. But how do you check that in a chip? In a chip, once it's fabricated, you cannot check those things. You want to tap internal to chip and find out a certain thing is zero, a certain place is one. It's not possible, because this is like a block where you cannot tap inside. Now, in order to tap inside is something which we do is known as design for test. The design for test is gives you an ability, kind of ability to tap inside the chip and make sure whatever is supposed to be zero is zero, whatever is supposed to be one is one. Okay. After that, what we do is physical design. Okay, physical design involves multiple steps. You partition the design. If the design is too big, you floor plan, do the floor planning. Floor planning is more like, let's say you're, so building a chip is like you building a city or building a house, right? So you'll figure out, okay, let's say you're building a city. You will figure out where gardens would be, where roads would be, where apartments would be, where markets would be. So that's like partitioning and floor planning, and then placing those places there, then connecting the roads, connect the main supplies, those was like clock tree synthesis and routing. And then you do a timing closure. Make just timing closure is just a fancy word of making sure you are meeting setup and hold timing, which you have learned in college, in each and every flop. And then you do physical verification. So let's understand some of these steps. Floor planning is, okay, figuring out where I'll be placing logical block, where I'll be placing RAM, where I'll be putting other parts of the chips. Then I will first connect, one of the most important part of the chip is clock. Clock is like a heartbeat of the chip. Heartbeat, as in without this, nothing will function. So you figure out, okay, how I will make sure clock goes to each and every flop in the design, and that is known as clock tree synthesis. Then you connect all the other connectivities like AND gate inputs, A input, B input, where it should connect. Those are connected using wires, and that is known as routing. Then you do timing closure, which is nothing but making sure every flop in the design is meeting setup and hold timing. Then do physical verification. In order for device to be fabricated, there are some restrictions in terms of minimum width, minimum separation, minimum overlap. Those have to be made sure. These are provided by the foundry, and this is what is known as physical verification, so that you will be able to actually fabricate the chip. If there is a question, if any of these fails, which team will deal with this? So there, in chip design flow, right, as in there are multiple steps where you do, let's say RTL design, RTL person is designing RTL, there will be verification team which is verifying it. Static timing analysis, the place and route will do a place and route, while static timing analysis will verify that. So there is no single, typically there is no single point of failures in the chip. Whatever you do, it's checked double or triply by multiple tools in the flow. So then you do fabrication, as in you would have learned these steps, lithography, then basically etching the device, and then doing a deposition. So basically fabricate the chip. Then you last stage in the production of semiconductor devices is is basically you cover it in a package. Package is like an encasement to protect, and then you ship it out as a chip. But before you ship it out, you actually have to do testing. You make sure the chip is working. And there is a question: can the chip fail? Yeah, chip can fail. A lot of time chips fail. Sometimes these, if this fails, then you can fix what using something known as engineering change order. So there is a question: suppose clock tree synthesis is failed, which team will resolve this? So let's understand the meaning of failure, right? When you're doing clock tree synthesis, you're connecting wires to every part of the clock. So the meaning of failure is that clock is not connected. Tools will automatically check that clock is connected, and it will issue errors or warnings when the clock is not connected. So there are tools which the same place and route tool will team will ensure that these steps are done properly. And then you do testing. Testing is very important. You don't want to ship a product which is failing, and whatever we did in DFT is used to test the chips here. And then once testing is done, then you basically give it to the customer. So we talked about, right, there are multiple components, multiple like processors, memories. So let's understand what are the, like, let's put it in Indian context. What are the opportunities which exist there? Or, and this generally applies to globe as well. So there are design companies which have fabrication, like you can think about Intel, right? Intel is one company which has fabrication. Then there are design companies which are fabless, which we don't do their own fabrication. For example, NVIDIA is one such company, right? Then there are foundry or fabs. Intel, for example, TSMC, you would have heard about Global Foundries. These are companies which fabricate the chips. Then there are IP vendors, for example, which create a small component of, let's say, chip. Let's say, for example, someone just designs a 5G modem or just designs a processor. Those are known as IP vendors. Then there are EDA companies in the ecosystem, which actually are software companies, which, as I said, right? So EDA software is like a compiler for chip design. They convert your logic into gates. Design services, some design, these are the companies which if you come from the understand from the software, like TCS, Infosys, which provide services, do certain projects, because there is a lot of resource requirements, and some of these resource requirements are not full time. So then design services kind of come in and do these support requirement. Then there is system design. When a chip iPhone is made, there is work to be done at system level as well. There has to be OS on the chip, so that comes pure embedded and software kind of work. The companies which do that. Then there's, of course, after fabrication is done, you assemble, package the chip, connect, if let's say on a board or however the package has to be connected. So there are companies in that. So semiconductor system and it has all that. So semiconductor also has software, as in if it's a misconception that it's purely hardware work, most of this is software work as well. Then some of the terminologies you would have heard about: tape out. Tape out means, as in the design side work is done, it's and then basically it goes to the fabrication or foundry. Then metal is when the metal fix is done. Then you would have heard about system on chip, when you have multiple complex components connected together. So SoC is one of the term you would hear. Then PPA, power, performance, and area. This is how you basically typically judge how good a chip is. Wafer, there is a silicon wafer on which chip is fabricated. ASIC, specific application specific integrated circuit. You'd create chips for certain specific applications. Low power, you want to ensure power is low. So this is one of the terminologies you'll hear. STA, static timing analysis. DV means design verification. That's another terminology you will typically hear. PD stands for physical design, the back-end part of the chip design. PV, physical verification. You make sure as a chip can be fabricated by following certain rules and guidelines. DFT, design for test. How you tap the chips? How do you create structure so that chip can be tested later? That is known as DFT or design for test. And FPGA, as in there are chips which are created in foundries, but they're field programmable. These are reprogrammable chips. That's also known as FPGA. That's another terminology which is used. Silicon, you would have heard about silicon. So these are the certain terminologies. Now, what are the opportunities in chip design? Before that, let me check. There was a question. Sometimes congestion comes in the netlist run. So you mean in the physical design congestion comes. So you have to reorganize. You have to figure out what blocks are connected, where what have more connection, maybe place them close to each other. So that's the step you have to do to avoid congestion. So what are the opportunities in chip design? There is chip opportunities in analog design, which is like more like your circuit design, which you would have learned in college. Then there is in analog, there is design, there is layout, there is characterization, there is IP and memory design, there is electronic design automation, there is CAD. So these are the multiple job opportunities which exist: circuit design and simulation, cell characterization, memory design and characterization, IP design and characterization, run set development, CAD and methodology, analog layout, and EDA related like application engineering, product engineering, R&D, which is software and sales. So these are multiple opportunities which exist in analog side of the world. And let's talk about digital side of the world. There is front end opportunity where you do RTL design or verification. There is back end opportunities where you do physical design, EDA, of course. So you have RTL design and verification. You have design implementation, physical design, static timing analysis and timing, physical verification. These typically are done by engineers or teams which specifically focus on one aspect of the work: low power, DFT, then again EDA related application engineering. So lot of opportunities, both digital side, front end side. So why should you join semiconductor or chip design world? You actually can create real products which you can touch and feel. It's related field, it's in your core field related to what you learn in college. And if I can say something, right, as in it's best when you stay in core field because the chances of growth are much more than, let's say, if you are an electrical engineer and going to do IT, and you work on the latest cutting edge technology. Like you talk about AI, as in AI is enabled, machine learning is enabled by all these chips which we are designing. And compared to other careers, your growth is faster, you get better packages. Initially, maybe if you're not from a very good college, or maybe not percentage, the package may be low, but then basically move to faster growth in the package. So congestion is so as I said, congestion is not linked to RTL design. Congestion is linked to how wires are connected. So RTL engineers don't have to do anything. Physical design engineers have to fix the congestion. Okay. So why join? There are more than 1 trillion chips that were shipped globally. So it's the fastest growing market. Washing machines, medical equipments, aeroplanes, consoles, computers, cars, refrigerators, smartphone, TVs, every device, everything use the chip. And it's going to grow further. By 2030. It's expected to be 1 trillion market, which will be close to double of what it is today. There is new industry, 5G technology, maybe 6G, cloud computing, AI, smart cities, smart devices, multiple existing electronics, and there is requirement for multiple more kind of devices which are coming. And India stands in a unique position. One, because of the talent we have, number of engineers we have. It's your responsibility as engineers to train well so that you can make for yourself. And also because of geopolitical situation, things happening with China and other countries. So India has a unique position to grow in this area. And that's why we are uniquely poised to make the best use of it if we focus on it. There are multiple career opportunities: design, manufacturing, R&D, sales and marketing, for undergraduates, for postgraduates, for researchers, for technicians, even for business graduates on the sales and MBA side. There are plenty of jobs. As it's estimated, there are around 1.25 lakh jobs in next 5 years. Initial salaries in MNCs are really good, and even in services company it's becoming good. And even if your initial salary is not good, the growth is one of the fastest compared to any other industry, so you'll be able to pick up very fast. So this is what I wanted to cover. We at VLSI Deep Dive are a basically online training company. So I'll just share what we do. Just a minute, let me share my screen again. Okay, so we are at VLSI Deep Dive, a training company. We provide a comprehensive learning platform. We provide various kind of learning materials, workshops, boot camps. So we have a lot of conceptual videos and courses, which is like Udemy, where you can purchase a course and learn for yourself. Or we have something live webinars and workshops. These live webinars and workshops are typically 1 or 2 days or 4 days, where basically you get either to participate in live webinars, or you take workshop where workshop has a recorded session. Plus you can ask your question there live, doubt solving session. Or we have boot camps, which are typically 3 to 4 weeks in a particular topic, where you have live classes, labs to be done, and it's these are the multi. We do have a free learners community channel. You can go to our LinkedIn page, or you can click here on WhatsApp link to find out what are the next workshop, boot camps, live webinars which are coming up. We do have a lot of offers. We have special offers for students and discounted prices. So please feel free to reach out to us if you need any course. You can see there are more than 50 to 60 courses. We have courses on RISC-V, front end, back end, SoC design, verification, formal verification, every topic of the VLSI we cover. So if you have any questions, you can visit our website, vlsideepdive.com. There is a WhatsApp link. You can click here to ask if anything specific you want to ask.